welcome friends to this second lecture of week 10. In this week we are talking about the retention of pollutants on and within the soil solid phases. In our previous lecture we have talked about the major forces which are responsible for retention of organic pollutants in the soil solid phases, basically the pollutants on the soil solid phases, and then we have discussed what are the mechanisms for attracting the pathogenic microorganisms onto the soil solid phase, and also we have started discussing about the negative adsorption. So, in the negative adsorption we have discussed that it is basically the repulsion between the between the ions from the similar charge surface, and this repulsion, this Coulombic repulsion is known as the negative adsorption. And also we have discussed the relationship of given by the scientist Posito, where we can mathematically quantify the excess of moles of ions per unit area of suspended solid. So, in today's lecture we are going to extend the discussion on negative adsorption, and we will also see what are the other factors which are responsible for for retention of non-ionic pollutants onto the soil solid surface. So, let us go ahead and see, we have already seen this relationship given by this Posito in our last class, and we are going to so what is we are going to discuss some more about the negative adsorption. Now, negative adsorption, we know that if an anion approaches a charged surface, it is subjected to attraction by positively charged sides of the surface or repulsion by the negatively charged ones. Obviously, most of the times the negative charge in the clay surface develop due to isomorphous substitution or sometime due to the pH of the surrounding medium. Now, when the negative charge develop on the surface of the clay particles, if an anion approaches to that negatively charged clay particle, it will face a Coulombic repulsion force or negative adsorption, and if the surface is positively charged, then obviously it will these negatively charged anions will be electrostatically attracted. Now, since clay minerals in soil are normally negatively charged, anions tends to be repelled from the mineral surface. For example, we have seen that if a dilute neutral solution of potassium chloride is added to a dry clay, then the equilibrium chloride concentration in the bulk solution will be greater than that of chloride concentration in the solution originally added to the clay. So, basically the clay is negatively charged. So, when we add this potassium chloride, which is dissociated to potassium ion and chloride ion, the concentration of the chloride will be higher in the bulk solution than that of the or which is originally added to the clay due to this negative adsorption. Now, this process occurring when an anion is added to a dry colloid with no adsorption capacity for the anion at the prevailing pH is called negative adsorption. So, now I hope you are clear about the negative adsorption. Now, it is related to the unequal ion distribution in the diffuse double layer charge colloids. Obviously, there is an unequal distribution in the diffuse double layer charge colloids. So, obviously, that is why there is a repulsion. Anion negative adsorption is basically affected by certain factors. These factors is the anion charge, then concentration, then pH, then presence of other anions and the nature and charge of the surface. So, these are the major important things which impact the anion negative adsorption. Now, negative adsorption in the soil can is basically decreases as the soil pH decreases. So, when the soil pH decreases, negative adsorption decreases, and when the anions can be adsorbed by positively charged soil or soil colloids. So, obviously, negative adsorption will be decreased when the pH decreases. Why? Because when the pH decreases, obviously there will be formation of positively charged positively pH dependent charge. As a result of that, there will be attraction between these anions as well as the positively charged surface, resulting in reducing the negative adsorption. Similarly, when anions can be adsorbed by positively charged soils or soil colloids. So, these are two conditions in which we can see reduction of negative adsorption. The greater the negative charge on this of the surface, the greater is the anion negative adsorption. Obviously, the greater the negative charge of the surface. So, that is why we have seen we have discussed that the charge of the anion is charge of the anion is important. So, greater is the negative charge of the surface, greater is the anion negative adsorption. Acidic toxic organic compounds in their anionic form are expected to be repelled by negatively charged clay colloids. Obviously, acidic toxic anionic compounds in their anionic form are expected to be repelled by the negatively charged clay surface. Now, amorphous clays also have some pH dependent positive charge at low pH values. Under such condition, most acidic organics are in the molecular form in the soil, so that the significant adsorption by formation of anionic bond is improbable. So, again during this under such conditions, most acidic organics are in the molecular form in the soil. So, that significant adsorption by the formation of anionic bond is improbable, because we have seen that acidic toxic organic compounds in their anionic forms are being repelled by negatively charged clay surfaces. Okay. So, the adsorption of, so we have discussed the adsorption of ionic pollutants. Now, we are going to discuss the adsorption of non-ionic pollutants. Now, remember that the adsorption of non-ionic pollutants on the soil solid phase surface is subjected to a series of mechanisms. What are those mechanisms? The mechanisms are protonation, water bridging, cation bridging, ligand exchange, hydrogen bonding and van der Waals interaction. So, we are going to discuss them in the coming slide. So, if we consider the non-ionic pollutants, what are the important non-ionic pollutants? In this class of pollutants, hundreds of compounds belonging are basically chemically different group, like as you can see here, it is chlorinated hydrocarbons, then organophosphates, then carbamates, ureas, anilines and anylides, amides, etc. So, these are the examples of non-ionic pollutants. Now, the great differences between the properties of these groups and among compounds within a group are reflected in the variability or the adsorption mechanism, and soil organic colloids plays a dominant role in this process. So, obviously, all these compounds are basically non-ionic pollutants, and also among these compounds are also the properties vary so widely that their adsorption mechanism onto the soil organic colloids play and their adsorption mechanisms as well as the presence of soil organic colloids plays an important role in the process of their adsorption or retention. So, these two scientists known Hassett and Burnworth in 1989, they considered that the sorption of nonpolar organics by soil is due to the enthalpy related and entropy related adsorption forces. So, there are two types of forces, one is enthalpy related, another is entropy related adsorptive forces. Now, these two scientists, they consider that sorption occurs when the free energy of the sorption reaction is negative. So, this free energy that is denoted by this delta G, which is basically uh, the difference between this delta H minus T into delta S. So, this is when this delta G is negative, then we can and only the when this delta G is negative, then only the sorption occurs. Okay. So, the free energy of the sorption reaction can be negative because of either enthalpy term at the entropy term or the contribution from the both. Okay. So, these negative sign of this free energy can stem from either the enthalpy term or the entropy term or the combination of the both. Okay. Now, the enthalpy term is primarily a function of the difference in the bonding between the adsorbing surface and the sorbate, or in other words solute, and that between the solvent and the solute. So, the entropy term on the other hand is related to the increase and decrease in the ordering of the system upon sorption. Okay. So, these are the two terms which basically plays the major role for controlling the adsorption of non-ionic pollutants. And remember that the sorption occurs only when the free energy of the sorption reaction is negative, which is denoted by delta G, and this negative free energy can be the contributory the contributory process for this negative free energy can be either enthalpy related process or entropy related process or the contribution from both the processes. So, for a chemical reaction at equilibrium, the free energy, which is denoted again by delta G, can be calculated from the equilibrium constant K. We have already discussed equilibrium constant in our previous lecture. So, or thermodynamic equilibrium constant, if you remember. So, the enthalpy change, which is denoted by this delta H. So, this delta H is basically the enthalpy change, can be calculated from the variation of K with temperature, and delta S can be calculated as the difference. So, basically this delta S is equal to delta H, which is enthalpy change minus change in the free energy by the divided by the temperature. So, this delta S can be calculated by using this formula. Okay. So, let us see the enthalpy related adsorption forces. Hydrogen bonding can be considered as one of the major enthalpy related adsorption force. So, let us see what is hydrogen bonding. Hydrogen bonding, which refers to the electrostatic interaction between a hydrogen atom covalently bound to one electronegative atom, that is oxygen, and to other electronegative atom or group of atom in a molecule. So, here you can see this is the hydrogen bonding which is occurring between this hydrogen atom as well as this electronegative oxygen atom. Now, this hydrogen atom may thus be regarded as a bridge between electronegative atoms. So, obviously, you can see this is an oxygen electronegative atom, this oxygen is another electronegative atom. So, this hydrogen is acting as a bridge between these two electronegative atoms. Generally, this bonding is conceived as an as an induced dipole phenomena. Obviously, positive and negative dipole. So, obviously, there is an induced dipole phenomena. The H bond is considered, the hydrogen bond is considered generally as the asymmetrical distribution of the first electron of the H atom induced by the various electronegative atoms. So, due to the presence of this electronegative atom oxygen, there is an induced asymmetrical distribution of the first electron of the hydrogen atom, and as a result there is an electrostatic attraction. So, this is called hydrogen bonding. We have discussed the hydrogen bonding while discussing the clay mineral structure, if you remember. If you remember the interlayer interlayer bonding between the kaolinite structure has a as a hydrogen bonding. As a result, they are having the collapse structure and their nutrient poor, low internal surface area. So, this hydrogen bonding plays an important role for different clay structure also. Now, another important process is the ligand exchange process. Ligand exchange process involves the replacement of one or more ligand by the adsorbing species. Now, we have discussed ligand in details. So, I am not going to discuss it further, but remember that in some instances the ligand exchange process can be regarded as the condensation reaction, which is for example, reaction between a carboxyl group and a hydroxy aluminum surface. Under some condition, this ligand exchange reaction are very likely to be involved when the humic substance interact with the clay mineral. So, this is how the sometime these organic pollutants get adsorbed onto the clay surface, this ligand exchange process. Another important process which is controlled by enthalpy related adsorptive forces is the protonation process. Now, what is protonation mechanism? The mechanism of protonation includes a Coulomb electrostatic force resulting from charged surface. Now, the development of surface acidity by solid surface of the soil offers the possibility that solids having proton selective organic functional groups can be adsorbed through a protonation reaction. Now, we know by the definition of acid that the acid is a proton donor. Okay. So, the development of a surface acidity, when there is a surface acidity by the solid surface of the soil. So, solid surface, when there is a surface acidity, so that in exchange it can donate a proton to that solid which having a proton selective organic functional groups. So, as a result of that there is an adsorption, and this is the perfect example of protonation reaction. Another bonding is known as the pi bond, and you can see the figure here of pi bond here. So, pi bond are covalent chemical bonds where two lobes of an orbital on one atom overlaps with the two lobes of an orbital on another atom, and this overlap occurs laterally. As you can see here, two lobes of one atom is overlapping with two lobes of another atom, and this overlapping is basically occurring laterally. So, this is an example of pi bond, and this mechanism can be used to explain the bonding of alkenes, alkylines and then aromatic compounds to soil organic matter. So, this is another important enthalpy related adsorptive forces. The next one is London van der Waals forces. We have discussed some van der Waals force while discussing the diffuse double layer, but remember that this London van der Waals force is a relatively weak electric force that attract neutral molecules to one another in gases, in liquefied and solidified gases, and in almost all organic liquids and solids. So, basically there is a here you can see there are neutral molecules, and these neutral molecules are neutral molecules when they instantaneous, when there is an instantaneous dipole on A induced a dipole on B, then there is an attraction. So, that is called the London van der Waals forces. So, in this A, when there is an instantaneously dipole on A, you can see positive and there is negative. So, positive charge, negative charge. So, there is a dipole. So, instantaneous dipole when results in a dipole in B also, then so here is a negative, positive, and due to this dipole, instantaneous dipole, there is a opposite sign develop in the vicinity of the B. So, you can see here there is another induced dipole also. So, this is an example, this is the reason for this van der Waals force. So, these forces are generally multiple, that is dipole dipole or dipole induced dipole. So, you can see here dipole induced dipole interaction produced by correlation between fluctuating induced multiple moments in two nearly unchanged polar molecules. So, here you can see two unchanged polar molecules, okay, for unchanged polar molecules, and there is a instantaneous dipole, and as a result of that there is a induced dipole in the second molecule. So, obviously, there is an attraction. So, this is called the London van der Waals force. Okay. So, this is another important enthalpy related force. So, despite the fact that this time average induced multiple in each of the molecule is 0, the correlation between the two induced moment does not average 0. So, as a result of this induced dipole, an attractive interaction between the two is produced at very small molecular distance. Now, remember that this is very important. So, this van der Waals force basically occurs at very small molecular distance due to this induced dipole between the two polar molecules. So, this is one of the important example of enthalpy related adsorptive force, which plays a very important role in the adsorption or retention of pollutants onto the soil solid surface. Now, the next important enthalpy related adsorptive force is chemisorption. There are two types of sorption, one is called chemisorption and this is physisorption. However, let us only focus on chemisorption here. Now, chemisorption is the short form of chemical adsorption. This is an adsorption in which the forces involved are valence forces of the same kind of those operating in the formation of chemical compounds. Now, it has got some specific features. This chemisorption has some specific features, as you can see. One is the phenomenon is characterized by chemical specificity, it is very chemically specific. Second, the elementary step in chemisorption often involves activation energy. Third one is chemisorption may not be reversible. As far as the specificity is concerned, this picture shows it more clearly. In case of there is a two example here, one is physisorption and chemisorption. In case of physisorption, we cannot see any specific binding site. However, in case of chemisorption, for the substrate surface, we can see there is a specific binding site in which the solutes are getting attached. So, this is the example of chemisorption, and this is an example of specificity of chemisorption. Okay. So, we have discussed all the enthalpy related forces. Let us also discuss the entropy related adsorptive forces. Now, the entropy related adsorptive force is also known as hydrophobic sorption. Hydrophobic sorption. So, it is the partitioning of nonpolar organic out of the polar aqueous phase onto hydrophobic surface in the soil, where they are retained through dispersion forces. Again, it is the partitioning of nonpolar organics out of the polar aqueous phases onto the hydrophobic surfaces in the soil. So, where the hydrophobic surfaces in the soil occurs? Maybe in the organic matter. So, in the organic matter, this hydrophobic surface, they can partition out, they can separate out these nonpolar organic compounds from their polar aqueous phase and help their retention into the soil. So, this is known as hydrophobic sorption. Now, this figure basically shows the diagram, or this diagram basically shows the forces which are contributing to the sorption of hydrophobic organics. So, here you can see for example, this is a organic pollutant, this is a nonpolar organic pollutant, and it is their polar aqueous phase. Okay. So, these small black dots are basically water solvating polar groups, okay, and also these are highly structured water. Okay. Now, you can see here is the soil organic matter, the nonpolar moiety is attached and the polar aqueous phase is facing forces favoring solvation. So, obviously, here the polar aqueous phase or polar phase is facing the forces favoring the solvation, because here the solvent is normal bulk water. So, this is normal bulk water. So, obviously, this polar phase will feel the affinity towards this normal bulk water, which is a polar, water is polar. So, obviously, there will be an attraction of this polar phase for solvation in this aqueous phase. However, this non-polar moiety will feel a force opposing the solvation, obviously, because this is hydrophobic in nature. And you can see here the hydrophobic sorption is occurring in the onto the soil organic matter, which is by default hydrophobic in nature. So, this soil organic matter has the capacity to separate out this non-polar moiety from its mixture of the polar aqueous phase, and this is known as hydrophobic sorption. Now, also you can see the similar things in some soil minerals where this non-polar moiety will be adsorbed, and obviously the polar phase will try to go out and then try to be favor the solvation process in the polar aqueous phase. The major feature of hydrophobic sorption is the weak interaction between the solid and the solvent. Obviously, here the solvent is the water, normal bulk water. So, the solute is non-polar moiety or organic pollutant. So, obviously, there is a very weak interaction between them. So, the primary force in hydrophobic sorption appears to be the large entropy change resulting from the removal of the solute from the solution. So, we can see when the solute from the solution is changed, there is a large entropy change, and this is the primary primary force in the hydrophobic sorption. Okay. The entropy change is largely due to the destruction of the cavity occupied by the solute in the solvent and the destruction of the structured water shell surrounding the solvated organic. So, basically when the cavities in the cavities in the solvent which are occupied by the solute get destructed by this separating force, then obviously there is a entropy change. And hydrophobic sorption, being an entropy driven process, provides the major contribution to sorption of hydrophobic pollutants in the soil surface. So, obviously, this entropy related force, entropy related adsorptive force is a major force for adsorption of organic pollutants onto the soil surface. Okay. I hope that you have learned something new in this lecture. Let us wrap up this lecture here, and in the third lecture we will be discussing adsorption from from the complex mixture or multiple mixture and other important aspects of the interaction between or the retention of the pollutants onto the soil solid surface. And if you find any difficulty, please let me know. I will be more than happy to answer your queries, and I hope that we will gather more comprehensive knowledge. You will get a more comprehensive knowledge once we complete this week of lectures. Thank you very much. Let us meet in our next lecture.